So, what I want to talk about is Euretos. So first of all, my name is Davy Suvee. I work as a big data architect for data management team. Euretos Brain is not really our product, it's not something that we created for a client. Euretos is a startup company here in the Netherlands, and what they're trying to solve is somewhat similar. It's in a biological network, so try to bring together various types of biological data. Not really for the bioinformatician guy, but more for an end user, so really the researcher that is just going through papers and all kinds of stuff and tries to bring these data together and tries to understand what it's about. So to give a concrete use case, so as some of you probably know, in PubMed there's around 23 million medical publications, and each day around 1,300 on average are added. So this means that lots of new articles are in there. So it's kind of a challenge for a researcher to really read all of that stuff, or at least try to find the research that could be relevant for him. The only thing that they really have is a Google-like interface. You can type in some keywords and then hope to find something that could be of use to him. Now, so imagine that the researcher is reading an article and he reads that malaria is transferred by mosquitoes, and he's a stupid researcher, he didn't really know that. So and all of a sudden he has thought like, okay, could you show me other publications that have that similar concept inside of it? So if you go to PubMed, this is how PubMed looks. It's a little bit like Google, so you have a search bar on top. This is the paper that the guy was reading. Now he has a few opportunities now. The first thing he can do, of course, is to go to the authors themselves. Probably the authors have really similar publications around the same concept. There's around 10 authors here, they each have 20, 30 publications, so that's again 300 publications to read, which is a lot of work. The next thing that he could do is just go to the references. Of course, the guy who wrote this paper, or who wrote this paper, of course didn't read the 23 million other publications. And also references are maybe not always that fair. So the only thing that you can do is, on top of the search bar, write malaria and mosquito, and then search for it, and then you see you get around 10,000 papers, and then you can start reading for a couple of years to come back. So that's a little bit a problem. So what the guys of Euretos and Brain, what they try to do is to bring together various types of medical data sets. Not only data from PubMed, but from others like Euretos and that kind of stuff. But give a very easy to access user interface. That's the core idea. Now, everything involves around a noun. A noun is basically, the idea would be to publish your information in the smallest piece of that makes your research relevant. So instead of having an abstract, do it in a more structured way. And the way how that is done is basically in assertions. So for guys who know RDF, it's kind of similar to RDF. You have subject, predicate, object. So in this case, malaria is transferred by mosquito. But this is only the knowledge itself. But it's also, of course, important, and which is also a cool topic, is the provenance. So who said it, in which paper was it published, which author said it, so that you can find like that information. Now, as most of you know, if you look at malaria, and you look at various databases, it's all encoded in different ways. So if you would look at PubMed, it's just called malaria. But if you look at some other database, it's called P22384, and yet another database is called AQA79. It's all fictitious. It's not real, but that's what generally happens. So the problem is, if you use more RDF kind of technology, is that the researcher itself is responsible for doing these mappings. If he goes from database 1 to database 2, he needs to know that malaria is basically called P22834. If he goes to yet the other database, he again needs to do the migration. Which for an end user, for really the end user who has no clue about all these mappings and how this is done, it's quite a tedious task. So what Euretos basically has done is somehow the other way, through an ETL process, take all these various types of data sources, which are XML, JSON, RDF also, all kinds of stuff, MySQL dumps and that kind of stuff. Try to come up with a data model that makes sure that if we are looking at the same content, for instance malaria, that malaria exists as a concept only once in the database. So that you don't need to deal with these other three guys. Now, internally, you still make sure that you can find the synonyms so that you can go back to them. But internally, within the system itself, as an end user, you're only looking at malaria, or the synonym that makes the most sense to them. Now, if you do that, you get a very nice network, because you get kind of like a biological knowledge network. You have, for instance, malaria that is transferred by mosquitoes. But as all databases refer to the same mosquito and all databases refer to the same malaria, we basically have a big knowledge network of everything that is related to it. So, it's like the Google knowledge graph and Facebook knowledge graph, something like that, but for biological data. The cool thing is also, if you use a graph below, that you can easily go from the node on the top end to the node really at the bottom. And so you can do shortest path calculations very easily, very fast in Neo4j, because we're using Neo4j on the covers. And we can go very fast from one node to the other, which is a little bit more difficult to achieve in a more RDF context. So, Brain itself, it's available, people can subscribe for it. It basically has two use cases. At the one hand side, there's exploration. You start from a concept, you start from a triple publication, and you want to traverse in all kinds of directions. But there's also some analysis involved, going from one node to the other. Or for instance, if you have two nodes, predict the chance that these two nodes could be connected. The idea is that pharma companies could say, like, apparently there's no research being done purely in that space, but what's the chance that there would be a useful connection between these two nodes? We try to integrate as many data sources as possible, some there. From an architectural side, what we have done is, we have different types of entities. We have compounds, we have diseases, we have animals, we have all kinds of stuff. Trying to create a database model that would be able to fit all of that in a kind of schema way would be a very hard task. And also, each time when a new data source comes in, we would need to refactor or do all kinds of data migration. So we didn't really want to go that way. So as a result, all metadata stored about each entity is stored in MongoDB. I will give it the reason why we do that later on. The graph itself, so the knowledge graph that I showed you, that's stored in Neo4j. Basically, Neo4j itself, or the graph database that we are using, only stores the nodes and the relationships. All the attributes that are given to nodes or relationships are stored in MongoDB. And what we also have is we have REST endpoints, which is kind of logical. We've written a swing interface on top of it, which maybe seem a little bit crazy to some people, but it's a startup company. They didn't have the money to really build an entire web application with all bells and whistles that people typically expect. So as a result, we wrote a swing application. Now, how does it work, or how does it look? It looks something like this, which is very blurry for you guys. The idea is that you have workspaces. A workspace is basically an experimentation environment in which you're working. You want to find nodes, find relationships, add them to them, find these publications, that kind of stuff. And the idea is that you combine everything in a workspace and you run analysis on top of that. Now, in order to find a particular concept, you have a search window on the top there. You can find on triples, so concept, relation, concept, or only on relation, only on one concept at the other side. And we use Solr on the covers in order to quickly find particular nodes. So if you start typing malaria, you kind of have like a Google suggest kind of feeling to it, so you start typing it and the possible matches are immediately shown. So imagine you're typing in malaria. In that moment in time, you basically get back a result. But there's various types of malaria thingies. There's malaria compound or diseases, there's malaria medicine, there's malaria mosquitoes, there's all kinds of malaria stuff. So as you can see, well, you cannot really see it, but you need to read. There's like an entire hierarchy or a classification involved into it, so that you can easily filter to it and say, like, okay, I'm not interested in diseases, but only in medicines and that kind of stuff. So imagine the first thing there is algae malaria, and you didn't really know what algae malaria is, you're interested into it. What you can do is click on it and open a detail screen. Now this is how the detail screen looks. You have algae malaria in the middle, and the visualization basically shows you all the triples that are associated with it. So this means, I think there's around 50 triples or something like that associated with algae malaria. So these are the 50 pieces of knowledge that we have in our database that are known. From here, people could navigate. They can find a node that they're interested in, click on the node, and basically extend the graph and see how they can navigate through it and go in all kinds of directions. So there's a little bit of serendipity effect involved. Now, if people would do a query, they selected algae malaria and yet another type of malaria for black water fever. They can click on it and say, like, find me the triples. This is the screen that you get. It's basically, the view has changed a little bit, but it's basically an enumeration of all triples that match your query. And the last one is kind of interesting. It says that black water fever causes kidney failure. So imagine that you don't know that as a researcher and you know or like to know who said it. You can basically click on the triple. This is the detailed view of the triple. It's basically just a triple. That's spectacular. But what you can also see at the site, if you can read very well, are basically the publications. So what kind of meta publications have this piece of knowledge inside of it? The cool thing here is that you can also see also the authors, so you can click on the authors and see all the publications that are in our system about them. Or you can click on the publication itself. And basically the view changes at this moment in time. This publication has multiple nanopubs associated with it. It's not only one, the one that we saw, but many. So as a result, I think there's around 10 or 11 triples associated with it. The visualization also makes sure that you can again see the links between it. So like some of them are like highly interconnected. So from here on you can again go forward, select a particular triple, try to see what the triple is about, and basically navigate and click and click and click and try to find stuff that is interesting for you. It's really targeted towards the not the not technical end users. They cannot write queries themselves in Cypher or that kind of stuff. It's more on the exploration side, but we try to give them or functionalities to do analysis. One of the analyses that we support is doing shortest path, as I already mentioned. And now we had a little bit of a problem there in the sense that we have to deal with supernodes, so nodes that have lots of relationships associated with it quite frequently. So for instance, you have two diseases. You have AIDS dementia complex and you have Malaya avian. And if you're looking at the data itself and you say like, okay, what could possibly be between it? It's for most of all diseases it says patient or it says water or that kind of stuff. So it's not that interesting, and because we try to give them an analysis that gives them an insight, but it gives them an insight they already know. That's not really the purpose. So what we've done in order to circumvent this is to assign values to each relationship. So the more unique a relationship is, and that depends basically on the number of times the relationship itself is being used, or the number of times the nodes in the relationship are being used, we give it a value. And the lower your value, the more important, well, not more important because that's not what statistics say, the more interesting the relationship is with respect to the total database. So at the moment when we're doing shortest path calculations, we take into account this value and we basically return the shortest path. So really also on the value level. So as a result, if you would read very well, there's some kind of treatment that sits in between. Now, I cannot really explain what the treatment is about, but for them it's more interesting. So it's treatment shared by two diseases, which could be of interest to the researcher on the cases. What we also support as a mechanism, you have these boxes. We support kind of a visual query builder, where on each node you can say like, okay, I'm only interested in things that have this particular type of measures, or who are of this type of entity. And some of the boxes can be empty, some of the boxes can be filtered. And then it's kind of like a visual cipher query, if you want to call it like that. You basically are building a pattern and you ask like, okay, find and search in the database. Because at this moment when you do shortest path, they don't really have any control over it. It's just find the cheapest path. So it's not really, for them there's not really a role of control. If they can use a visual builder, saying for particular boxes which things should be filtered and which not, gives them a lot of power. So if you look at the database itself, because they do a lot of deduplication, both at the level of the concepts, but also at the level of the relationships, the data is still quite manageable. Yeah? So we have around 6 million nodes and 20 million relationships inside of the database. We still run it on a single Neo4j instance, and it scales quite well. So we don't really have a problem on the performance level. There were a little bit of problems. In the beginning, we tried to do everything in Neo4j, so also storing the properties, so all the properties that we had about a particular node. Sometimes it's a little bit more complex because within Neo4j you can store key-value pairs, but sometimes we wanted to go a little bit deeper, so key with a value and value that has again values and that kind of stuff, which is not really easy to do in Neo4j. But also, if you wanted to do a more complex search to find basically a start node from which to do our query, for instance, find all nodes or relationships of a particular type where a particular property has more than a particular value z, that wasn't really fast in Neo4j. So that's the reason why we store all our metadata about a particular node in MongoDB, because it's much faster to get to the initial nodes. So we do a query in MongoDB, we basically get back the nodes as a starting point, and then you go to the graph to really start to reset. Yeah, as I already said, we frequently encounter the curse of the supernode, because there's many nodes that have a lot of, well, there's not really many nodes that have a lot of relationships. I think maybe only half a percentage has above 10,000 relationships and more. But if you hit them frequently, and then everything blows up. So as a result, what we currently do for some analysis is that if a particular node is above a certain degree, we just don't take it into consideration. So we hit it and say, okay, let's not bother about it. It's a limitation of the system, but it's also the only thing that makes it manageable at some point, because otherwise people are waiting forever to get their results back, which is also not the purpose. And the final thing, and something that we found is that, as I already mentioned, we are giving, we are attributing values to each node and to each relationship to take into account data analytics. When we are adding new data to the graph, this has basically an impact, because the degree of a particular node goes up. So as a result, also the value that we are associating with nodes are going up or down. The problem is that we didn't find, we looked at a system which is called Reco4j, which is like a plugin on top of Neo4j that allows you to do recommendations, and also has the statistical information inside of it, so that if you do something on a particular node, everything around it is automatically updated. But it didn't really suit our use case very well, because we had other types of analytics. So what we currently are doing is that if we update the data, we basically have a batch process that goes over all the statistical information and tries to update it. But sometimes we're updating stuff that shouldn't be updated at all, while recalculating it shouldn't be done. So we do it in a batch-oriented process. It would be kind of cool if we had a mechanism to do it more, I call it inline, but to have it more like within the graph database itself as a call mechanism. I'm looking at you that you're coming closer.
Yes, thank you. Thanks. Short questions, right?
How much of your effort went into data integration?
But basically, the main tool that you saw now was quickly developed. Yeah. Most of the time is indeed on data integration.
Well, are you aware of linked live data?
Sorry?
The site linked live data. Well, it's a public service that we keep. Integrates about 30 of these important open data sources in life sciences.
Mm-hmm.
It has about 1 billion nodes and about 6-7 billion relations. Mm-hmm. Actually, that's relations plus properties, so it's not directly comparable to your model, but I would say it's probably 1,000 times bigger.
But we're also dealing with it, it's not only data that is available in the public, but also the end, or the target of this product is also smaller or bigger pharma biotech companies. The idea is that they can also integrate their own data.
Well, we have clients that do it, AstraZeneca, LDBC. But I think that the large pharmaceuticals are now of the mind that this is commodity data and they're cooperating to build it up and deploy it and so on. And there are projects like ClarkSea, where we produce it, and OpenFacts, where openly.
Well, we're building basically on OpenFacts. So the first database, or the concept wiki database that has been created by OpenFacts, is basically the basis from where we start. So we use their data as a bootstrap environment. So not to start from zero, but to have something that is already in place. And basically all the data that is not currently not in OpenFacts, we basically add it ourselves through the same mechanism.
I'm not sure how the data in OpenFacts compares to linked live data, but I think you should also take a look at that.
Right.
I think they have overlap. But okay, so you have these. You want to do some kind of operation on the whole graph to get the connection weights. And to do that, what kind of algorithm? Is it like a PageRank type thing where you?
That's a PageRank type of stuff. Yeah.
Right. Okay. So you want for us to benchmark stuff that is of interest to you. You would like us to benchmark PageRanks, similar things that is.
But in this case, the performance of it is not that important, because when the data is added, it's okay if it takes a few.
Sure. But having this kind of off-the-shelf in a DBMS would be something you consider valuable.
Well, it shouldn't be part of the core. It would be nice if kind of a plugin would be provided like Rico4j that allows you to do this kind of stuff, so that you are not basically recalculating everything within the graph like we currently do, because we just go over everything and we don't do it in an incremental fashion. We just do it all the database.
I would be interested in knowing more about the shortest path queries that you do. So they are formulated over pre-calculated weights.
Yes. So we try to do it on the fly, but that was not a go. So we pre-calculate all the weights. Once the weights are there and the graph doesn't change, we can do whatever we want.
Right.
But at the moment when you have new rows, new relationships, the game changes and you need to recalculate, because it's not that, in general, it's not that if you add a new node or relationship that everything changes more in a specific context, but still things change, so you need to update it.
It would be cool to have some of these source factors that you have and you use and use them as examples. Okay. I think we have to go to the